All right, good evening, fellow people. We are here to talk about deep learning with imagery and 3D data. Now, throughout the week, there was a lot that was done with deep learning, with geospatial AI. You've seen some of the work that we've done with AI assistants as well. But something I'd like to really call out, Ishmael has talked about this, the entire team has talked about is geospatial AI. We've had this going for a few years already. This is in production, and this capability has really matured over time. So today we're going to show you what exists today, what is available for you to purchase today, what you can work with today. And more specifically, we're going to talk about imagery and 3D. I'm Vinay Vishwambaran. I'm a product manager on the imagery team. I look into the imagery suite of products and I look at AI. Weber, if you want to introduce yourself.
So I work in GeoAI team. I'm also a product engineer. So I mostly work on 3D deep learning, imagery, and text. Yeah.
All right. So first, a quick primer on what is geospatial AI or what is GeoAI. Now, over the most recent times, machines have been able to do a lot of things. They can see, read, understand, learn, and adapt, analyze data sets, and even create data sets. Now, with GeoAI essentially is kind of the intersection of both the science of GIS and AI. It's bringing the two components together. And our machines with GeoAI capabilities, you can now do tasks like land cover classification, detecting objects, point cloud classification, essentially see objects, see features within data sets. Likewise, you can do things like entity extraction, text classification, perform tasks like text to shape, and you can learn and adapt from existing data sets using AutoDL, techniques like AutoDL. You can refine AI models. You can perform analysis like clustering, classification, prediction, regression, so on and so forth, several machine learning tools which you've seen within our system already. And lastly, using generative models, you can actually create data. An interesting data set here is we got Sentinel imagery that was covered by cloud, and using generative models, we were able to eliminate clouds from that image. So that was, kind of a quick primer on GeoAI. Now, you'll see that I've interchangeably, especially in these slides, I've interchangeably used the terms deep learning and GeoAI. Over these more recent years, deep learning is seen to be the most prevalent or a more prevalent technique of AI. And that's why, I put it into the same bucket and I interchangeably use the term AI and deep learning. So honing in on deep learning within ArcGIS, there are three key data structures. There's text, and I talked about entity extraction, text classification, and everything. These are tasks that are possible on textual data sets. Likewise, we've got vector and tabular data sets. There are several tasks that you can perform on that. And lastly, imagery and remote sensing is the third data structure that is supported natively within ArcGIS. And in the imagery and remote sensing bucket, we have a whole suite of data modalities which we'll talk about, including 3D and point cloud. So I will be covering a lot on core imagery. I'll be talking a lot more about core imagery, while Weber will be talking a little more on 3D and point cloud capabilities that's within the system. But again, this is going to be more conversational. And given the size of the crowd, I'd like to keep it conversational both ways, right? You guys feel free to jump in, ask questions as well, but not more than one question per person. Okay, diving into imagery. So like I said, we support all modalities of imagery that is natively supported within ArcGIS, and essentially all of our capabilities like object detection, image enhancement, 3D object detection, object classification, all of these different capabilities can be run, or all of these different tasks, they can be run on these different data modalities. So for instance, I can do object detection on street view images. That's more recent. And you can do point cloud classification, 3D object detection, all of this on 3D data as well. And then I can work with video, and you can do tasks like object tracking or multi-object tracking. So initially, probably a couple years ago, 3 years ago, I think so, we started off with just object detection and overhead imagery, but as you can see, the system has really evolved. There are multiple model types or model architectures that are natively supported for the 5 key tasks that are available within ArcGIS. Pixel classification, here you have a collection of model architectures that are supported. Likewise, object detection, instance segmentation, image classification, and image translation. Now you might ask me, yeah, I've got about 10 different models. What's the point? It is a double-edged sword, yes, because the data scientists, developers, and those of you who worked with deep learning quite a bit, you'll have a good understanding of a lot of these model architectures, and you know when you're supposed to use each model, right? But again, it's a double-edged sword. Some cases, I'm new to deep learning, I just need to extract features. Which model do I use? So for that reason, we've added something called AutoDL, which is auto deep learning. It'll determine the best possible model for you, so you don't have to worry about all of this. We've got a whole slew of backbones as well, so it determines the optimum backbone to be used as well. And like I said, there are 5 key tasks when it comes to imagery. There's classification, detection, segmentation, and here, image translation. Image translation is basically transforming your image from one domain to another. Simple examples are SAR to optical, or optical to SAR, or optical imagery to elevation data sets without really photogrammetrically deriving those elevation sources. Of course, here I've shown an interesting example of how we've converted an image with horses to zebras. I don't know why would somebody want to do that, but hey, it was a fun exercise. But yeah, we've got a series of models which will enable you to do a whole slew of tasks, including under image translation, we have something which is super resolution, which is pretty interesting.
Yeah, so when it comes to 3D deep learning, within 3D deep learning, we support 2 kinds of tasks. One is point cloud classification and the recently added 3D object detection. So both of these are available in the release version of Pro. And digging deeper, if we talk about architecture, so for point cloud classification, we have point CNN, RandLinit, and SQNseg. I can go into details in the later parts of the presentation. And when it comes to object detection, we have Detection 3D, where the architecture is called Second, and we are looking into adding more architectures for 3D deep learning in general, both in point cloud classification and object detection.
All right, this slide, I just want to tell you, where does GeoAI or where does deep learning show up within ArcGIS? At the heart of it, we have the Python API. The Python API essentially is designed for a developer, it's designed for the data scientist, and it gives you access to all of the parameters and everything. You can tweak hyperparameters, there's much more that you can do. The next level of abstraction is the ArcGIS tools. And when I say tools here, I mean geoprocessing tools, which you guys are familiar with. And we have other tools like Deep Learning Studio, which I'll talk about a little more. And the last level of abstraction is pre-trained models. With pre-trained models, what we're trying to do is really simplify or make it really easy for our users to get into the AI domain, right? Get your feet wet. Just pick a model for different business reasons, pick an imagery source or a data source, and run our inferencing tools, and we'll extract meaningful information for you. So this slide talks a little more about the pre-trained models. We started off with just one model, which extracted building footprints. We wanted to get a feel of the market and see, what was the adoption like. Quickly, there was a lot of traction. We had a lot of interest in that model. And because of that, we ended up, over the past couple years, we increased that library of models, and we've got more than 72 different models that are available within the Living Atlas. You can download these models, work with it directly within Pro, work with it within Enterprise, or you can use ArcGIS Online directly to consume these models and run inferencing. And the beauty of these models, you can even fine-tune them to your geography, or you can fine-tune them to the imagery that you have. Now, if you noticed, they're all segmented into different sectors over here, because increasingly we realized we can actually have models that are catering to these different sectors. So essentially, we've got models that cater each and every sector that Esri works in. We've got models specific to state and local government, public safety, transportation, utilities, so on and so forth. Now I'll go over a quick journey of some of the models that are available. To start with, you head over to the Living Atlas, and here, like I said, you have access to more than 70 different pre-trained models. Different business tasks, right? Some just to create a foundational GIS layer, like in this case, Building Footprint USA. You can create or extract building footprints from high resolution imagery, 8-bit imagery. And the thing about these models, you click on these models, it provides you with descriptions of the models. Why is it relevant? Who is it developed for? We provide you with a guide. In the guide, you have easy access to all of the information, which tells you on how to use, it gives you information about how to use these different models. Here we have an understanding of the input. It provides you with an understanding of the input data sets that are required, the cell sizes, and what will the output look like. Why is my mouse? Okay. Here we also give you information about the model architecture, and another question which we're constantly hit by is our users want to know what is the accuracy of these models, what is the precision, recall, F1 score. All of this information is provided alongside the model. And then we provide you with a few screenshots so you have an understanding of what the model really represents and what can it provide you. Here's an interesting example. I got about 60 gigabytes worth of imagery from the country of Grenada, and they asked us to create a foundational GIS, right? Extract a bunch of features. And next, they said the country is susceptible to floods, it's susceptible to landslides. So can you create an information model? Can you create a map for us, a landslide susceptibility map for us, and show us infrastructure that is potentially at risk? So we went ahead and using tools within ArcGIS Online, raster analysis, deep learning, detect objects, pick your imagery layer. It's the imagery that we hosted. Here I have access to all the models that I have trained myself, or that is available on my organization, or I can go directly to the Living Atlas. Living Atlas, you have access to all of these models that I talked about. Pick this here, run the analysis, and you're good to go. Obviously, in the interest of time, I'm not going to run the tool, but I'll just show you the results that we extracted. So for instance, here we've extracted building footprints for the entire country. We've extracted roads, and we've created a land cover map as well, right? So this is kind of the foundational GIS layers which they requested us to create. The next level is solving that problem of landslide susceptibility. So using raster functions, using image processing algorithms that is available out of the box in ArcGIS Pro, in ArcGIS Online, we created a landslide susceptibility map. And this is what it looked like. Right now I brought all of those layers into 3D, into my scene view, so I have better context. And here when I zoom into this layer, here you can clearly see infrastructure that is at risk. These roads, these houses are safe, and there's a hotel over here, God bless them, they're all at risk over here. Okay. The next, we got high resolution imagery from Maxar. And again, using online, I went ahead, extracted roads, then we extracted palms, extracted trees, and we extracted buildings. Now, the real value here that we want to call out is not just feature extraction. What we've done here is we extracted features as just polygons, and once we got the polygons, we attributed them using City Engine rules. So you see what's happening here. We've got a complete end-to-end system where you use ArcGIS for extracting features, and then you use ArcGIS for providing rules and attribution to each one of these features so that you can bring these features to life. But you got something cool to show as well, right? So he took this to the next level. He does a bunch of stuff which is really, really cool. He puts me to shame, but go ahead.
Yeah, so when I showed you the whole view or the whole scene in a web map, but what I did actually is use the whole content and use the ArcGIS game engine SDK and brought everything into the game engine and created a flyby here. So let me just play this. And we can see and visualize this in a much better way. And this can also be used with the, I mean, with AR and VR, so you can use that. And with game engine, the new opportunities also come into play, like urban planning and whatnot. Now, moving ahead, just to understand the power of pre-trained models. In 3D, we have two pre-trained models on Living Atlas. One is directed towards utility customers, which is power line classification model. And here are some of the results. And then another is tree point classification model, which does the same thing, but for 3 points, and it can classify the 3 points within any scene. So here's an urban scene, and it's a forest scene here. Now, using these two pre-trained models, next I'll show you how to solve a huge problem with utility customers, which is vegetation encroachment. And it's a very relevant problem these days, along with, I mean, not only just with utility customers, but also in terms of vegetation management on a city level, you can use these pre-trained models. So here we have a whole citywide data set of roads and nearby areas with the roads where we have power lines and trees. And this is Ballard City in Australia. We used our pre-trained models and classified the power lines and trees for the whole city. And along with that, we also classified ground and building points. After classifying, we were interested in where these encroachments are happening for these power lines, and where these vegetations are either intersecting, or if it's close to the power lines, or if it's above the power lines. So by doing some analysis in Pro via GIS tools and a model builder workflow, we were easily able to identify 3 types of encroachment: above, intertwined, and below. Let's check some of these examples now. So this is a good example of where the vegetation is above the power lines, and this is very critical in cases of a storm where this tree can very easily fall and it can cause a power outage. Just for better visualization, I've color-coded them here. So even this is another example. Now let's check another type of encroachment, which is intertwined, where the tree or the vegetation is within the power lines, and it's going. Let me just maybe show some other views. Yeah, so you can see it's basically getting inside the power line. So this is also very risky in terms of managing this vegetation, and which can cause power outage. This is another example where I have color-coded it for better understanding. Now the last type is basically when the vegetation is growing below. So it might cause an issue in future, but yeah, so maybe not that immediate attention is needed for these kind of encroachment, but yes, we can detect that also. And here is the last example where I have color-coded the same thing. Yeah, over to you.
All right. So some of y'all have probably heard, again, we got this segment anything model. It was defined by, or it was created by Meta. So what we did is we took that model and then we wrapped it as a deep learning package. So users can actually download that and they can work with that deep learning package within ArcGIS. It's pretty slick in that, you know, if there are any features in there that really just stands out from the background, it picks it up immediately. So in this case, it could delineate yachts. And it's not text prompts particularly, it's just segment the image and it gives you a bunch of segments which you need to attribute. Here we got agricultural fields, but the model is rather stupid in the sense when you have a bunch of features like this, it segments everything. So there's no notion of geography, there's no context, there's no nothing. So it can get a little challenging for the model. So what we did is we went on ahead and we combined two models to create the text SAM model. And here essentially I can provide an imagery, I can provide an image, and that model is available on the Living Atlas. Search for it, text SAM. You can specify text, free-form text, like literally in this case I'm providing trailers. It's going to run this. Let's take a look at the results. And this is literally running on my machine, it's running live, it's running right now. It's a fairly small area, and there, it's just extracted all of the features. So I could just change this into planes, yachts, anything. It's just free form text, and it's going to extract these features for me. So it's kind of an enhancement that we've done over SAM. We've essentially combined SAM with another model called Dino to enable you to just enter prompts and work with it within ArcGIS. That is also available in GitHub. We've posted it online, so you can download it, check out the code, make modifications to it as required. Next is we've also gone ahead and fine-tuned, using low-rank adaptation techniques. You can now fine-tune your SAM model as well. So here's an example of what we've done. I've taken building footprints, and in this particular case, what I want to do is I've taken elevation data sets and I want to extract building footprints from that. So essentially what I've done is typically SAM is designed to work with RGB imagery, true color imagery, but we're fine-tuning this so that it works with elevation data, so that it works with multispectral imagery, which is more than 3 bands, and it can work with SAR as well. So once I've done this, I go through the process. Here I can take a look at the results. Let's overlay this now in a map, and here you can see the results. So yeah, we've exposed this. You can fine-tune the SAM model as well. So that was I wouldn't say a quick tour, but that was a tour of all the pre-trained models that we've added into the system. After pre-trained models, we had tools, which I told you was the next level of abstraction. This was done for GIS analysts, for 3D analysts, for the image analysts, essentially who want to train their own models, right? There are 2 use cases here. One is you want to train your own models from scratch. You have your own use cases. 2 is, and we've had a few customers, we've had a few partners who did this, and we put their models on the Living Atlas as well. This particular scenario was one of our distributors from Saudi Arabia. They took our building footprint US, building footprints US deep learning model or deep learning package. They ran it on their imagery in Saudi Arabia. It was a holy mess. But then they added just a handful of training samples and fine-tuned that model to their geography and their imagery. They got excellent results. So these tools, they enable you to fine-tune those models. They enable you to even create your own models from scratch. Now we've got tools within ArcGIS Pro. It's exposed through Image Analyst. It's exposed through 3D Analyst. And then we've got tools which will enable you to perform these kinds of tasks on full motion video. And lastly, we've got Deep Learning Studio as well, which is kind of an end-to-end web application. I'll talk a little bit about that in a bit. So Deep Learning Studio is essentially a web application. It's an end-to-end web application for enabling you to perform various deep learning tasks. How many of y'all have image server here? Okay. How many of y'all have deep learning studio? Okay, I don't understand the math, because if you have image server, you have deep learning studio. The image server guys didn't raise their hands for deep learning. The deep learning studio guy didn't raise his hands for image server. But just to let you know, if you're an EA customer, you have image server. If you have image server, you have deep learning studio. So as for the licensing mechanism, by default, any user who has image server, you have access to deep learning studio. Deep Learning Studio, the whole premise of the Deep Learning Studio app is to enable you to collaborate, right? When do you use deep learning? It's not when you need to capture 5 training samples and run and train a tiny model and run inferencing on a single image. It's usually done when you have large amounts of images, a lot of training that needs to be done. For that purpose, you can manage a whole deep learning project on your enterprise. You can scale out your your capturing of training data, your QA of training data, and then you can have multiple contributors to train a deep learning model and run inferencing as and when they want, leveraging a cluster of machines that's available on your enterprise. So that's the premise, or that's the purpose of Deep Learning Studio. And it's a thin app, right? It's a lightweight app, which you just run on a thin client. So we can all deploy it on our different machines, while enterprise is hosting the app, and it's using existing data models like the feature service and an image service behind the scenes. It maintains your chips in a data store. I have a quick demonstration of this. So this is what the app looks like. By default, as soon as you open the app through the app launcher, it gives you a list of all the projects that you have. Oops. It gives you a list of all the projects that you have, or you could go ahead and you can create a new project. In this case, you can see all the projects that you have on the left tab, on the right tab. There's shared projects. If you have projects that are shared with you, you will see those projects as well. So in this case, we can go ahead and we can create a new model, a new project. We're doing this for manhole detection. You can pick the object type, so project type. In this case, it's object detection. Once it's done, step 1 is preparing your training data. You have any one of these 3 options to go with. We start with preparing training data. And the system knows it's not configured as yet, so you have to pick the target image service or the source image service you want to work with. You define the schema of your training samples. In this case, we're detecting manholes. And then who do you want to share this group? Who do you want to share this with? You specify the group and you define a grid. So each grid can be allocated to different people. So different people, different teams can work on capturing training data. Next step is obviously collecting training samples. So this is a uniquely tailored experience so that you can capture training samples. You come in here, pick all of your training samples. And once you're done, hit done. You can review the training samples, and at this point it brings up a dashboard for you. And you can step through each one of the training samples. And you can either approve them, this seems fine, this seems fine. We can reject this one. Complete. Once you're done, you can even manage your image chips. Here we can see all the chips that we have if needed. Or we go ahead and we train a new model. Click New Iteration, pick your image chips folder. It's very similar to the workflow that we have in Pro. Here you define your max number of epochs and additional parameters as you define in Pro. And you kick off the training. Once you're done with the training, you see the model metrics over here, and you can save this model, and it's stored directly within your enterprise. It's stored on your portal. You bring up the inferencing dialog, and here you can pick a model that you want to run inferencing on. specify your input imagery layer, your area of interest, and you can kick off the process. And here you go. These are the results. Cool. So that was in the interest of time. Obviously, I had to show you the whole thing through video. But that is kind of an overview of the Deep Learning Studio. I'll do a quick demonstration of a workflow within Pro as well. Now, in Pro, we have a collection of geoprocessing tools for imagery, 3D, and we have a set of tools for text as well, text and tabular data. In this case, I'll just quickly show you an imagery workflow. So if you get into the image analyst toolset, under deep learning, you have all of the tools that I was talking about. Right, the scenario here is the Woolsey fires, and we worked with USAA, insurance company, and what they wanted to do was when the Woolsey fires broke out, they wanted to disburse insurance claims to their customers as soon as they could. And it was a challenge. They had more than 10,000 building footprints. They had to review these buildings and look out for the buildings that were damaged and the ones that were not damaged. So step one is we captured a bunch of training samples, about 800 training samples, and we've got tools which will enable you to do that. So for instance, here you can head over to Imagery Deep Learning Tools. Label objects for deep learning will enable you to label different objects. It's a experience that is designed specifically. It's an editing experience, but it's designed specifically for labeling training data. And once you're done with that, you can go call export training data. And the export training data tool, essentially, it looks at each one of these features, and it creates little chips. Let me just pull that up. You can specify your input raster, your input feature, which is your training sample right now, and a field. In this case, the field defines damaged and undamaged, and then additional parameters such as the tile size, so that because you're planning on creating chips over here, which you're going to feed into the system so that you can train a model. And lastly, you need to specify the metadata format. This is important because based on the task you're trying to do, you need specific types of metadata. There's a little bit of the documentation here, and we have this documented in our documentation, Core Pro documentation as well. So once you run this, you get a bunch of chips. You reach out to the next tool, which is your Train Deep Learning Model tool. Specify your input training data, which is those chips. You specify an output folder where you specify your deep learning package. It's going to be output over there. Here, like I told you, you can use a pre-trained model if you want to start from something that has been trained before, and then you can pick your model type. Here we have a collection of models to pick from, and you'll notice I have object detection, another object detection, another object detection. So which one do I choose? Now, if you're familiar with this, if you're experienced with this, you would know, right? Each one of them, they have their flaws. So if you're okay with more false positives, you can go for one. More false negatives, you can go with another. If speed is what is important to you, you can go with another. But on the flip side, we also have train using AutoDL. That'll automatically let you pick. It'll automatically choose a model for you. You just have to provide the input training data, let it run for a few hours, and it'll let you pick the training data. Lastly, you run inferencing. In this case, it's classify objects. I provide my images, I provide my buildings feature class, and I ran inferencing, and this is what the results look like. It's classified 10,000 building structures as damaged and undamaged. And zooming in a little tighter, here you can see our buildings here, which are automatically classified. It's probably better than that of a trained assessor. And the model, it actually converged to about 99%, 97% accuracy. Now again, going back to the value of doing this within ArcGIS, it's not just extracting features. Once we've extracted features, in this particular case, I took it into Network Analyst and used that as barriers, the damaged structures as barriers, and then we could identify areas where we could drop shelters that are within 20-minute walk time for anybody who's affected. And lastly, we could share that out as a feature service. We could enrich that as a feature service and then bring that into a configurable dashboard. For any given region, you can see the total number of damaged buildings, undamaged structures, and the average damaged building value, right? So that was an end-to-end workflow where you could see how we went through the deep learning process. The images that we used was managed using image server, so large volumes of imagery. The onus of managing the imagery is not on the user. It's served out by a service. It's served out by a server. All you have to work with is a web service. You bring it in, you run your deep learning tasks, you run your feature assessment, network analysis, you bring it in here, and you can share this with stakeholders. So before I hand it over to him, quickly I'll just go over through some of the productivity enhancements that we've made. AI-assisted labeling. Labeling is daunting. It's a challenging task. So here we've done something where you can just click through each one of the different features and it automatically detects the feature for you. And this is essentially just labeling your data. Next is training a model. Like I talked about, auto deep learning. This is the traditional tool. You have to pick from a collection of different models. But what we've done is, and you've got a bunch of backbones over here, but what we've done with AutoDL is just provide your training data, and you can pick the neural networks you wanted to test. It'll test from this, and then it'll give you the most appropriate model for your data set. And lastly, inferencing, another optimization that we've added. Essentially, in one go, you can provide a single image, you can provide multiple models and geoprocessing models for workflows, and it gives you information products from a single tool. You want to go on with 3D?
So a little bit of revision before we move ahead. So yes, so we have two tasks within 3D deep learning. One is point cloud classification, and there is 3D object detection. Both work on point clouds. Architectures, we keep on adding new one after doing extensive research. So for point cloud classification, we have point CNN, Randall init, and SQnsig. So in terms of accuracy, all these three architectures can work well depending upon your use case. So you have to check which one works best for you. But in terms of performance, Randall init is the fastest among the three. So if you are looking for faster results, then you can go with Randall init. Now for object detection, we have added detection 3D support where the architecture name is second. This works really well with similarly sized object. So let's say if I'm not interested in the exact points which are to be classified, and I just want to know the vicinity of the object I'm interested in, then I'll go with 3D object detection. So as of now, we only have second, but in future, we are adding more architecture. Now let's check few of the examples which might be relevant for different users here. So here we have buildings and grounds. This is point cloud classification. Here we have trees and the background class. And here we have railway assets, and I'll go into that demo also later. And when it comes to object detection, we wanted to understand what's the number of cars. We were not interested in what the exact points which represent the car, so we kind of counted the number of cars in a parking lot. So here is that example for object detection. So, and here it's boats which are in a parking lot where you can kind of, it's a place where it's being sold. So yeah, that's why it's not ocean, but yeah.
Yeah, I was like, for a second, wait a minute, he's got boats in parking lot. Yeah, that's awesome.
Yeah, that's why I have to explain, yeah. So And here we have a synthetic point cloud, and we are detecting objects which are rooftops and tree. And of course, 3D object detection is very relevant for indoor point cloud, where most of the objects are similar size like chair, table, or fire alarms or fire extinguishers. Now, I'll be going through two demos where one I'll be talking about cars, where we'll detect cars, and I'll go through the step-by-step process, and where we follow the similar pattern which we use for point cloud classification using deep learning. And another demo, I'll be talking about railway asset extraction. I'll be going through the whole workflow, and this particular demo of railway asset extraction, it's actually a user story, and it was implemented for national government in the whole country. So I'll switch to Pro now. Let's first go through the 3D object detection demo. So we are already familiar with point cloud classification. So here, this is a scene where we have different classes like background, red is car, and brown is ground. Now coming to detection, is the same parking lot, but here we are not interested in the exact class codes of the point cloud, but we are interested in the vicinity of like where that object is. So it's just simple. We just have to create a multi-patch around those objects of interest. So this is my training data. And then following the similar pattern which we have in 3D Analyst extension, if you can just go down below. So we have the classification tools. The three tools, one for exporting, one for training, and then one for inferencing. And we also added one new tool to evaluate so that you can find the accuracy of your trained model in classification. And the same pattern goes with the detection, where first we prepare the data, then we train it, and then one tool is for inferencing. So in the training tool, in the preparation tool, first we provide our point cloud, and then we provide the 3 car volumes, which are actually multi-patches. And then the same goes for validation data. We provide our validation data and the validation multi-patches or volumes. And then we provide what's the block size, or it's the equivalent of tile in imagery. So it's basically what's the area on which we want the model to perform in an iterative way. So that's in this case, because our object is small, it's less than 50 meters, which is cars, so I went with a 50 meter of block size. Then we move to the next tool, which is training. So we'll use that exported data set, the exported training data, and then we use our second architecture, which is, the full form is partially embedded convolution detection, but we call it second in short. So so then we train the model, and the last step is detection. So here you can mention the confidence, overlap, and it will take care of the overlapping detections too, which are false, and we would want to likely to remove those. And the output is a multi-patch. Let's check that output now. So this is the result of a different parking lot, which is a test area, and we can see the cars are detected pretty well. So this is relevant when we are only interested in the vicinity of the object. And again, as I said, that it is very relevant for indoor. So
how many of you all use point cloud or 3D data? Isn't that awesome?
Nice.
Those little objects, we picked that out.
Yes, this is really cool. So this is an indoor scene, and we were able to detect the chairs. And if you can notice, this circular table is there, and then we have chairs, and these are 2 chairs they are detected. So object detection, please try that, and it's a new capability, and let us know. And we are constantly working on adding new architectures. Now, if we have time left, so I can move on to the next demo. So let me just first clarify the problem here. So basically, electric trains run, and they have a brush on top of it, which is connected with the wire. And if there is a slack in the wire, then that brush will get eroded. So getting the dimensions on a railway track is very important. So on the right, we are seeing those dimensions: top fitting, pole height, catenary height, contact height. These are very important for in terms of like maintaining the railway track and the assets and how the normal maintenance routines. So what we wanted to do here is extract these dimensions, and you will see how we'll use deep learning and our pre-trained models to extract these dimensions. So the first step is we already have a power line model, but this is not trained on railway power lines, so the geometry is different. But then also we used it on our railway lines, and we tried to figure out, okay, how the results are. And we found that the results are good, but there is a lot of, I would say, missed points. And because we want to be accurate with our measurements, so we thought that we'll fine tune it on this railway wires on this particular data set for so we'll label few kilometers of data set and we'll fine tune the same model, and then we'll see the results. So we did that. We manually classified 1 kilometers of data, and we fine tuned our power line model. And let me show you the results now. So here on the left, that's our input data. In between, we can see what we got from the power line model, which is not aimed for railway wires. And on the right, we can see the fine-tuned model output, where we fine-tuned. And you can see the results are really nice. Like now, I can actually do some GIS analysis and extract those measurements which we are interested in. Then moving forward, because it's not only the power lines and poles, but we were also interested in the cantilever, which is in yellow, and the railway tracks, which you can see in the purple. So these are also important assets because we wanted to find the center line and we wanted to find the contact height. So this is where I would say Pro's power really comes into play. So we used a model builder workflow using some GIS tools and analysis. We can go into the details later, but we extracted those dimensions from those assets which we classified using deep learning. So you can see we found pole height, we found center line, and then catenary height, contact height. We could actually find these values, and these are very relevant when maintaining these assets. And then top fitting and bottom fitting also. Yeah, over to you, Vinay. Let's switch that.
All right. So that was a real use case. It was one of our users, and you've probably seen it at one of our plenaries as well at the, I think it was at the last Dev Summit. These are inspiring use cases, and we really want to work with you guys as well. Reach forward if you have use cases, scenarios like this. We can work with you. If you want to get successful as well, if you run into hiccups or anything of the sorts, we're more than happy to help you. And likewise, I talked about the pre-trained models. We have more than 72 models. Majority of those models, we've actually worked with our account managers who've connected with customers. They've either provided us training data and said, hey, this is a generic problem which our industry, which our domain experts really want to solve. We are not necessarily the domain experts, right? You guys bring the domain expertise, and if you can drive a lot of this development, I think it'll really, really benefit us. It'll benefit the community, the entire GIS community, if you will. So to end this session, by now you probably must have noticed how our system, how ArcGIS is really an end-to-end geospatial AI system, specifically for imagery and remote sensing. Right on top, if you have raw imagery, we have the ability to process that imagery using reality. So you can process satellite imagery, drone imagery, aerial scans, and you can create 2D products, 3D products, 3D meshes, point cloud data, orthomosaic, so on and so forth. And then you can manage that using server technology that is available within ArcGIS. Again, you've just gone from one tech within ArcGIS stack, within the ArcGIS stack, to another tech, right? Once you're done with that, you prepare your data, you label your data, you train a model, and you deploy the model for production. You can run that at scale using RAST analytics, or you can use a SaaS-based environment and run this in ArcGIS Online. And lastly, we provide more than 2,000 geoprocessing tools which will enable you to perform downstream analysis, right? So you can take action on those results that you've derived, and once you're done, you can push it to a dashboard so that you could show it to additional stakeholders where required, or you could put it into workforce or other applications. So it's really an end-to-end geospatial AI system, if you may.
So,
Go
I think we have only like 10 minutes left. So,
Yep.
yeah, these are some of the resources.
Yeah,
And
these are some of the resources that we have.
and if you guys have some questions, so I can bring the mic and
Yeah, you can take a picture. A lot of cameras came up. And yeah, do share your feedback in the app. I've got 3 kids, he's got 2 kids, so keep that in mind when you're sharing your feedback. Questions?
Yeah, I'm wondering, is it also possible to include clips you don't want to the model to train? So exclude them.
Sorry, can you say that again?
So
Or Weber, you can respond if you can.
include clips you don't want the model to use.
So your question is, can you include clips that you don't want to use? Sorry, include chips that you don't want to use?
Chips.
Yeah, yeah, you can do that.
Yeah. Okay.
Hey, thanks for the slides. I found when you use these things operationally, they become stale quite quickly. And as a result, you have to continually train and improve them. And it looks like you're starting to develop tools to do that with
Can
the
you,
sort of...
sorry about that, can you hold the mic a little?
Sorry about that. I found using these things operationally, they become stale quite quickly. You do your best to train them to deal with as many circumstances as possible, but there's certain things you don't take into account. And then gradually the model becomes less relevant. So as a result, you have to continually retrain them. And there are ways of doing that. But have you got any best practices of doing that within the Esri suite?
1 second, I know I took 2 minutes of your time. But there's an echo for some reason, I think because the speakers are facing that way. If Weber, you got the question or?
yeah, so, okay, maybe I can answer that. So basically, yeah, you can find some resources. There are multiple blogs with tips and tricks. And I would say for imagery models, yes, we need to keep on updating them and fine-tuning them as soon as the geography keeps on changing. But if you talk about 3D models, so mostly the geometry remains same. The power line 10 years from now will also remain like that in terms of shape. So yes, with time, depending upon your object of interest, whether it's 3D or imagery, you can do that. Yeah, yeah.
Do you guys have, can you hear me properly?
You can take out the mic.
Okay.
That thing is echoing too much.
No, yeah, I mean, this one is very quickly. Do you guys have any recommendations for, I think we're gonna have feedback with that one. Any best practice or recommendations for high resolution imagery? I'm talking like about 0.5 centimeter rasters or like very, very high detail point clouds. Because when I work with that type of data, the performance ends up being very poor usually.
It is, yeah, it would be, you can add to that, you can expect to, so you're talking about high resolution imagery or you're talking about point cloud? Okay, in terms of high resolution imagery, it really depends on the problem that you're trying to solve. because many a time you really don't need that level of detail. So if you're trying to detect building footprints, 40 centimeters, 50 centimeters is more than enough. You said half a centimeter, right? So 5 millimeter. Oh, okay, that makes sense. Yeah, given the resolution of the data, it will take a lot of time. You just need heavy compute in that case. Cloud computing, high-end GPUs. I don't know, you want to add to that?
So for 3D, I would say you can resample, because with 3D, what happens is that like these days, the LiDAR sensor output are very dense point cloud, and it really becomes huge, like very fast. So I would say you can resample your point, and we have a really good tool within Pro, which is called thin loss. So you can, and there are multiple strategies. So you want thinning in a particular direction, X, Y, Z. You want thinning in a plane, or you want to keep the number of returns relevant in your data. So using those strategies, you can kind of reduce the size of your data, and which will also increase or help you in the performance while inferencing, or even during training. Yeah.
Yes.
Are there any deep learning tools that you can use outside of an enterprise environment?
All of the tools. So all of the tools that we showed, well, most of these capabilities are available in Pro, it's available in Enterprise, and it's available in online. So in Pro, you have all of those geoprocessing tools. In Enterprise, you have it as services, GP services, which you can hit. In online, you cannot train models, but you can run inferencing.
So it's not like an and situation, it's more of an or.
Exactly, exactly. But again, there's no reason, I could train a model in Pro, publish it to online, and then my organization could just use the model. We're good.
Thank you so much. Yeah.
Thank you.